Hello, and welcome to another wonderful lesson with Mr. Easy. Seniors, this is your last lesson of the year. Congratulations. Juniors, you got a couple more. Hang in there. But, last one of this chapter. So, last one kind of hitting with the next one's kind of hitting some trig. But here we're going to be applying how we can use those trig functions to find out information. So, starting with the kickoff here. So sine would give us an angle. Sine inverse would give us back, or this is an angle. Sorry, I'm getting ahead of myself. So this would give you a ratio. Sine inverse then would give you that angle back. Now, with sine inverse, our domain is negative pi over 2 to pi over 2. So 3 pi over 2 doesn't fit in that domain. However, what does 3 pi over 2 match up with? Well, it matches up with a negative pi over 2. And so that would be the angle we would get back. Because remember, as we go around, you'd be at pi over 2, 3 pi over 2, which is down here. Also, if we went down, we'd be at negative pi over 2. Because sine stays in this domain, this half circle, the right side of the unit circle. Getting into some application. So, from a point on level ground 125 feet from the base of a tower, the angle of elevation is 57.2 degrees. Approximate the height of the tower to the nearest foot. So a lot of times with these, it's going to be easier if you draw out the sketch so it'll help you visualize what's going on. So, if we're at a point on level ground, right here. We're going to be 125 feet away from a tower. So, tower. That angle of elevation up here then is 57.2 degrees, and this was 125. So we're looking for our height of our tower over here. Well, we have an opposite, we have an adjacent. Which one uses opposite and adjacent? Well, tangent or cotangent. Because cotangent's not on the calculator, I'm going to suggest let's cotangent. So we're going to set this up. Tangent 57.2 equals opposite x over adjacent 125. Well, to get x by itself, we would times both sides by 125 to get the 125 to cancel on the bottom. And that's what we're going to put in our calculator. Now, make sure when you're doing this, you go into mode first. Okay. Mine's in degrees. You want degrees to be highlighted because we're working with degrees here. Once you have that, go second quit. And we can put this in. 125 tan 57.2. Close your parenthesis. And we get 193.96. Which we're going to round up to 194. So, go through, read the problem, pull out the information you need, draw out that sketch, help you visualize what's going on. With this stuff, trig is going to be dealing with a lot of right angle stuff, so always try to make a right angle with this. We have our right angle there. Then we can use the trig functions, use the ratios, or if we need to use the inverses to find an angle, we can do that. So, a kite is going to fly at a height of 30 feet when 65 feet of string is out. If the string is in a straight line, find the angle that it makes with the ground. Round in the nearest 10th degree. So again, we're going to draw this out. So here's our dude. And he's holding the string to the kite. So at this point, there's our kite. So at this point, if we follow this straight down, we're going to be 30 feet in the air. This here is going to be 65 feet worth of string. So if we connect this back up, make our right angle, we can then find what it is with ground. Now, normally, if it's something like this, it makes it look like, okay, this guy's up in the air, this is where the string is, which if you're holding the string, you're not going to hold it on the ground. You're going to hold it up where your hand is. But a lot of times it'll say, hey, this is being held at this many feet above the ground. Always add that in at the end to get your extra height, because even if you follow it over here, this is going to be a horizontal with the ground. So you're going to be that high off the ground as well. But For this case, they're leaving that part out. They're just keeping it simple. So this is what we got. So we're looking for this angle over here. So if we're here, we have opposite, we have hypotenuse. Opposite hypotenuse is going to be sine. So sine of our angle, and a lot of times they'll use theta as the variable, just so you know that, hey, we're dealing with an angle here, we're not dealing with the side. This is all that's really doing. So sine theta would equal opposite, which is 30, over adjacent, which is 65. So we're going to do sine inverse of our ratio to get our theta. So second sine of 30 divided 65. Close it. If you wanted to go alpha y equals and get the fraction, you can do that too. Either way will work. And we get 27.48. A lot of times when you're doing this, you can round to the nearest tenth with angles. A lot of times they'll even round to the nearest whole degree. Either way will work. But because they said round to the nearest tenth, we're going to do that. So 27.5 degrees. So another place where they deal with this stuff is working with navigation and surveying. So they use bearing. Bearing is going to be the acute angle from the north-south line. So we have a letter, north or south, then the angle, and then another letter, east or west, telling how many degrees from the north-south line to the east or west. So like this next one here, it's north, 42 degrees east. So from the north, we're going to tip 42 degrees towards the east side. So north, we'll write this out, north, east, south, west, if you don't know your directions. Farm kids, you should all know your directions. If not, I may make fun of you. I mean, I'm not really going to make fun of you, but I might tease you a little bit. Anyways, so we have a boat that's leaving the entrance of the harbor, and it's traveling 25 miles on a bearing of north, 42 degrees east. After that, the captain turns 90 degrees clockwise and travels 18 miles on a bearing of south, 48 degrees east. At that time, how far is the boat to the nearest tenth of a mile from the harbor entrance? What is the bearing to the nearest tenth of a degree of the boat at the harbor entrance? So, making our sketch. Well, we could just use this. So, from the start, they're going north 42 degrees east. So, from the north, we're going to tip 42 degrees towards the east, and they're going for 25 miles. Then they're going to turn. Actually, let me draw a bigger one here. So north, east, south, west. Think never eat sour watermelon. That's how I learned it. So 42 degrees to the east. So we have this. This is 42. This was 25 miles. So then they're going to turn and go clockwise 90 degrees. So clockwise, we're turning this way. So making a 90 here. And they're going to go 18 miles. So if you think from the south, we'd be tipping 48 degrees east. So we're making 90 degree here. So everything going on. So what we want to know is, what is this distance? What is this here angle really? So if we do like a little thing here, this here is that 48. So everything. So what we're trying to find is we need to know this distance, and we need to know this here angle. So A is how far is the boat from the harbor entrance. So we're going to find the X here first. Well, if you think about it, we've got a 90-degree angle up here, which makes this into a right triangle. So we can use Pythagorean theorem to find our third side, our hypotenuse side. So for part A, we're going to do 18 squared plus 25 squared equaling our c squared. So in other words, our x squared. So I don't confuse you with another variable. Our x squared. We're looking for this. By the way, that was Pythagorean theorem that I'm using. A squared plus b squared equals c squared. This is supposed to be a 2. All right, so I don't know these off the top of my head. So 18 squared is going to be 324. 25 squared, I believe, is 625. And we are. So add those two together. So plus 324. We have 949. 949 equaling x squared. And to get x by itself, we would square root. So second square root 949. 30.8. So we want to the nearest tenth of a mile. So yeah, 30.8. X would equal 30.8 miles. So now we need the bearing to the nearest tenth of a degree. So we're going to find this angle here now. So again, we're not going to use our hypotenuse because we've rounded that. We want to use our exact numbers of 18 and 25. So from here, we would have opposite and we would have adjacent. Opposite and adjacent, tangent. So for part B, tan of our angle would equal 18 over 25. Opposite over the adjacent. So to find the angle, we do the inverse tan of the ratio. So second tan 18 divide 25. Close it. And we get 35.75. And they want nearest tenth of a degree. So 35.8 degrees. Now, that would just be from here to here. We're still in this upper quadrant here. So we're still tipping from the north. So really what we're going to have to do is we're going to have to add in the 42 degrees that are already here that were tilted, plus another 35 more. So if we add that in, plus 42, we'd be at 77.8 degrees. So the 42 tip into there, and then another 35 for the width of the triangle to get our full tip over. So we'd still be from the north, because we're up top here tipping this way. So north, 77.8 degrees. And then we're tipping to the east. So E. And that would be our bearing. So, moving on. So, another place where this gets used is simple harmonic motion. Simple harmonic motion is the up and down oscillations of things such as a spring. So if you think about it, if you have a spring here, and if you pull it down, it's going to pull it back up, and then it's going to pull back down again, and pull back up, pull back down, and it's just kind of going to bounce back and forth like this until it loses all of its energy. So think simple harmonic motion. Now here we're not worried about the whole air resistance, whatever you want to say, that could slow this down. So think if we're in a vacuum, that's simple harmonic motion. So really, if we pull this down, it's going to react opposite more, and then gravity will pull it back down, and then it'll pull it back up, gravity pull it back down, pull it back up, sort of thing. And so it's going to bounce back and forth. It's going to oscillate. So objects that move on a coordinate axis in a simple harmonic motion, if its distance from the origin d at time t is given by either d equals, so our amplitude there, or a, cosine of omega t, or distance equals our amplitude sine omega t. We're going to get into what omega here is in a little bit. I believe that's omega. I hope I'm not calling it the wrong thing. But this is where omega comes in. So motion has amplitude a. So that's how much up from, okay, so if a spring is just hanging there at rest, it's just here. That's our baseline. Amplitude comes in of how far down is it going to go, how far up is it going to go. So how much from this center line up, how much from the center line down is going to be your amplitude. So the period, so how long it takes to go up, down, back to center is 2 pi over omega, where omega has to be greater than 0. So that's the period for the motion to go through one complete cycle. So a ball in a spring is pulled 4 inches below rest position. That's going to be your A. The period of the motion is 6 seconds. So again, keep that in mind. We'll come back to that. Write the equation for the ball's simple harmonic motion. So I'm going to put P per period. Period we know is 2 pi over omega. Well, we have to use either D equals A cosine omega t or D equals A sine omega t. So first thing we're going to do, though, is find out what is omega, because we need omega in order to even do this. So if period is 6 seconds, we're going to put 6 in for P, and we have 2 pi over omega. So we would times by the omega, and then divide by 6 in order to get omega by itself. So dividing by 6, then we would have 2 pi over 6, which we could reduce to 1 and 3. So in other words, a pi over 3 will be our omega. Now, as far as sine and cosine, sine will start on that center line. Where cosine starts away. So if you go, and this is what I'm talking about here. So if we go to our graph, I'm going to go into my y equals, I'm going to clear out what I have. If I just go sine x, and if I hit graph, of course it's going to take a moment because I'm really zoomed out. So I'm going to zoom in. We're still not, okay, let me zoom in even more. All right, why are you not working? Let me go for sine x. All right, let me switch it over to radians. That might help. There. Okay, now I'm too close. Okay, sorry guys. So that's really what the sine wave is doing, is it's going to bounce back and forth from -1 to 1. But if you notice where we start here at the origin, we're starting on our line. That's where we're crossing. So we would go up, down, back would be 1 period. Let me zoom out just one more time. You can kind of see it a little better then. Okay, you're not going to see it better. Let me check just the window. Let's go zoom standard. Let's do that. There you go. So this is kind of what harmonic motion is going to look like. It's going to go up, go down, go up, go down, go up, go down, go up, go down, and just keep repeating that. So sine starts on the x-axis. It would go up, come down, come back up. This is some of what we missed skipping over 4, 5, and 4, 6, was going through and graphing all these out and how this all works. But it's really time consuming and it's very confusing, and definitely something that goes much better when I'm there to hit the questions as they come up instead of you trying to figure it all out on your own. So that is sine. So sine starts on. So now if I go back here and I do cosine, so now you'll see when we go past 0 here, we're not on our origin, we're up top. So we're away and we cross and come back top. So that's one period. So from the top down, up. So sine was here, went up, came down, went up. Here it's away, down, away. So that's how you kind of know. Now here it says it's pulled below rest. So we're starting below rest, which is why we want to use cosine. And because it's below, notice here how cosine starts up. To be below, we have to flip it by putting a negative in. So it's actually going to be d equals negative 4 cosine, our omega being pi over 3t. So if it says it's starting at rest, then you're going to use sine. But if it's going to be away from rest, if we're pulling it away, then we want to use cosine. That's going to be the difference between those two formulas. So another part of this is frequency. Frequency is the number of complete cycles per unit of time. So period is how long will it take for this to happen. Frequency is, well, every second, how often is this doing it? So they're kind of opposites of each other, of depending on what you're really looking for. Frequency, so think one place where frequency is with radio. The frequency that you adjust on your dial, so like 94.7 is the frequency. That's how many radio waves are going on. Radio waves, I think so. Radio waves that are going on per second. So they operate at different frequencies, so they dial into whatever frequency you're looking for. That's how the radio works. Little side bit. Anyways, frequency is the complete number of cycles per unit of time. So it's going to be the reciprocal then of the period. So if period was 2 pi over omega, frequency then is going to be omega over 2 pi. It's going to flip it over. It's going to be the reciprocal. Still can use your formulas for that, but that's just going to determine, that's just how you determine frequency compared to how you determine period. Again, period was 2 pi over omega. So let's find this stuff. A mass on a smooth table attached to a spring moves in simple harmonic motion described by d equals 10 cosine pi over 6t, with t measured in seconds and d in centimeters. So here they're going to give you the equation to begin with. Now we're going to pull information from it. Last time we were setting it up, here we're pulling it from it. So maximum displacement. So part A is finding amplitude, which is that A. So whatever's right in front, so if we look at, so if we had cosine here, A is what they're looking for. That's your displacement, whatever number's in front here. Our number in front is 10, so that would equal 10 centimeters. B now finding frequency. So frequency is equal to omega over 2 pi. Well, what's in front of the t is the omega. See, in front of t, omega. So that's what's going to go up here. So what we're really going to have is F equals pi over 6 over 2 pi. So we're going to leave change flip. So leave pi over 6, change to multiplication, flip this over to 1 over 2 pi. pi's can then cancel, and when we multiply, 1 and 1 makes 1, 6 and 2 make 12. So our frequency is 1/12 cycles per second. See now, is time required for 1 cycle? Well, all we have to do is flip over the period because it's the reciprocal. So period equals, or I mean of the frequency, sorry. So period would equal 12 seconds. So these two go really well. All you really got to do is find the one and then flip it over to get the other one. Makes that really nice. Amplitude, again, you're just looking what's in front of the trig function, whatever this number is. That's your A, your amplitude, your maximum displacement. So really, two of these are just look and write down. You're really just calculating the one. So that is it. If you have any questions, comments, concerns, please send me a message on Google Classroom. You can also email me or pan me, but know that I don't check the pans as often. So it might be a little longer before I get back to you. But again, if you're having some trouble, let me know, and I can try to help you out and explain stuff a little differently or a little more and get you on the right page. So until next time, guys, we'll talk to you later.